Hey guys, how's it going? Hey guys, let me know if you can hear me okay.
Yep, can hear you.
I
Can
can
hear
hear
you.
you.
You can? Okay,
Yep,
awesome.
no problems.
Perfect. It's always step number one here. Um, all right. So wait just another minute. I know Carrie can't make it tonight, but we'll see if there's anyone else that's gonna come in. Quick question for you guys. If like so I have not yet prepared material. Like I know basically what we want to do, but I haven't like made the homework or the readings yet for the next class. Partially because it kind of confuses me. Like I want to remember well what I'm talking about for each class, and if I prepare ahead, I get confused about which class is which. But when I don't think it should take me more than like 4 or 5 days to kind of have it up. But if I put up the stuff that you guys are needing to read and kind of watch or do in like, 4 or 5 days or so, I'm assuming that should give you enough time. Like if you have a little over a week to read,
Yeah,
like,
that's good.
is that
I mean, it's good
fine?
for me at least. I have no
Okay.
issue with that.
All right. All right. If anyone else has anything about it, that'd be awesome.
Oh, that'd be fine for me.
It's okay. Okay. I figure like if most people are like me, they're probably reading most of it like just a couple days ahead or
Yeah.
or pretty close to the actual meeting. But it definitely makes it easier for me to have a little bit of time. All right. So anyway, I am just going to record as usual. I put the last meeting up on YouTube. So if you guys, need the link to that, I mean, it's really just on the Contact a Gossip Guy YouTube where we have a lot of like training stuff. But basically, if anyone has to miss or, review or whatever for the actual test, if you're going to go do that, that everything will be up there. So yeah, so there was quite a bit of material this week, I would say. So, and I would say it's also like there was a fair amount of, math heavy stuff. As well. So, but then there was quite a bit that if you are, I'm sure if you're doing teching, but definitely if you're in optical, it was very, very applicable this week. Lots of stuff that, you're using every day, which is always cool because I do feel like a lot of this material can be, more on kind of the theoretical side or less on like the everyday kind of practice side of things. So we'll go through both things, talk about, everything. Obviously, there's a lot to get through on the optical side. So, if there are certain questions that you have or things that you need clarified on that, definitely let me know. But we'll try our hardest to kind of get through all of that. But what I asked you guys to do first was to look at book two. We're almost done with book two. I've tried to take book two, which is the basic optical principles book, a little bit slower because it is, again, quite heavy on the math side. And I wanted to make sure that we didn't try to do it all at one time, but there's really only a little bit left. It's not anything particularly crazy. It's just the very last part will be one of the things we'll tackle next meeting, but just a little bit more about that base in, base out prism and how that applies to Prentice's rule, which I think we went over. Really early on in our first meeting. So we'll review that briefly too, in case you've kind of forgotten a little bit about that. And then we did introduce optical cross stuff at the last meeting. So I did see a very nice picture, I think, of Sam going over that with I think with Carrie. So that's great. We can certainly review that too. I feel like that stuff is just, using it and practicing it. Um, on a regular basis. But okay, so anyway, with book two, I'm gonna share my screen so that we can just kind of have something to look at here while we are talking. If I can find where that is. Why does it not want to share? Oh, here it is. Okay, it's actually here. Okie dokie. So actually, hold on. I'm actually going to open up a new window because I want to basically just share this one window here. The ABO books one. Okay. All right, perfect. So, what you should be able to see is, and I'll try to just zoom in if it will let me a little bit. It doesn't seem to. Oh, there it goes. Okay. So anyway, what we are going through is basically we're going through the first part of what I asked you to read. And this also kind of applies to the readings a little. I'm sorry, to the audio recordings a little bit. The first part of the audio recording that I asked you guys to listen to goes into the metric system quite a bit. I know I had you guys read a little bit about that, or just go over a couple videos. Obviously, you're familiar with it already, but just kind of a little bit of review of it was stuff that we had done in some of the previous meetings. It also spent some time in the audio section going over positive, negative numbers, and really just kind of basic math principles. So obviously helpful to listen to. You may be super familiar with it, super well versed, but the some of the stuff that you encountered as the readings, as we progressed in the chapter, definitely relates a lot to converting from millimeters to centimeters to meters, and then backwards from meters to centimeters to millimeters. So that is definitely something you want to feel very, very confident with, with figuring out the diopter powers that we'll talk about later, and the focal lengths. That is stuff that can really trip you up, kind of silly mistake stuff that can happen on the multiple choice tests. We'll look at some practice questions, but what they, kind of try to do a little bit in the practice tests is they try to, it's not just doing the formula, it's also converting it into the correct measurement in order to do the formula or to find the correct answer. So definitely, you want to just not be thrown by that. So converting, and how many kind of decimal points to move over is going to really come into this. The next part of the reading, so anyway, sorry, this is kind of going over the math concepts that they talked about. Just gonna scroll through here. And then the stuff that I really wanted to focus a bit more on was talking about the visible lights, or I'm sorry, just the entire light spectrum. I will tell you that it's important for you to memorize certain parts of the spectrum, especially if you are going to go ahead and take the test. There are definitely questions about this on the test. So basically the things that you're going to really want to memorize is you're going to want to memorize what the light spectrum, the visible light spectrum is. There, I did find a little bit of variation for exactly from where to where they are, kind of saying the numbers go. Especially with blue light, I found a little bit of variation there. But in general, you're going to want to memorize, from 390 to about, or about 400 to about 750 is going to be nanometers. That's going to be the visible light spectrum. So those are definitely important areas that you want to, have in your head. And then they also mentioned that kind of the ultraviolet spectrum, that's going to be, they said specifically from 396 to 400. So, not part, of stuff that's easy to or that's visible to us, but definitely, there may be some questions about that too, on the exam. The one that we obviously spend a lot of time talking about is high energy blue light. So for blue light, we're considering that that's going to be from about 380 nanometers to 450. And that's something that I would say, I honestly don't know if there's going to be a question about the blue light spectrum or of where blue light is or where high energy blue light is on the spectrum for the test. But I really do encourage you to know, where that is, what those numbers are. Again, it's the 380 to 450 range. Just because that is something that comes up, in the office quite a bit, right? And if you can talk to a patient about, very specifically, these are the light rays, or this is light, high energy blue light, between 380 nanometers and 450 nanometers, it really gives the patient a strong confidence in you, right? And it really, is something that's going a lot more in depth, I think, than they would generally expect your knowledge to be. So that is, definitely something that I want you to encourage, that I encourage you to know. One other part of this chapter and the audio as well, it did talk a little bit about light waves, and that I would say is important for you to, have somewhat of an understanding of. It's going to come in a little bit later, when we talk about anti-reflective coatings and how those work. But basically, they did mention two different theories of light. They recommended, or I'm sorry, they mentioned, just the wave, and I think that is down. Where the heck is it? The wave theory, right? Where they kind of theorize that light moves in actual waves, kind of, like the ocean or water. And then there's the corpuscular theory, which is more that there are tiny particles of light, basically, and that originate from the light source. So, good things to know. I wouldn't worry too much about that, but it is good to kind of have those words, somewhere in your head, and have heard them before. Um, they do tell you very specifically here, they're giving you some very specific numbers here. I would not worry about memorizing like all of the different, light colors. I would focus mainly on, what is the visible spectrum. I think that's much more likely to be asked. And, I guess more for just knowledge within the office on a day-to-day basis, the blue light. So on that line of thinking, I'm gonna just pull up that PDF that I asked you guys to look at. It is the blue light document. Now, some of you guys may have seen this before. This is definitely something that we've looked at in sometimes the office meetings. I think we've used this. I know a couple years ago we did a training on it, but this is, really applicable to, again, to your day to day in the office, and talking about, why it's important, to filter blue light, and, to have a blue light coating, really. But the main points of this, that I think, I really want you to kind of take home from this PDF are that, even though we think of high energy blue light, or kind of as coming from devices or computers, far and away, the biggest source of it is sunlight. So, I think that, comes as a surprise to, our staff, but also to patients, right? They're not really thinking that they need to protect themselves outside with, with blue light. They kind of know about UV. That's become, very common knowledge. People, think about it. They know about sunscreen. They know about sunglasses and, UV rays. But I think that the blue light, the concept of that being, really prevalent outside is newer. So that's definitely something that I want you guys to really think about and be able to talk to patients about. There were some other things that I wanted to bring out. I can't remember exactly where it was in the document, but they talked about eye strain, and how it comes from blue light, and that it's actually oftentimes caused by not only like kind of the spectrum itself, but the flicker of the light can cause eye strain, over time being on a device. So that tends to, resonate with people. Also, something they don't often, come in knowing. I think, obviously the article touches on this. This is something that's a little bit more common knowledge, but sleep rhythm disturbances, that's another big thing that wearing a blue light coating or having a blue light filter will help regulate. So, not having, you know, not looking at a screen with blue light, or without some sort of filter, is very helpful for managing the sleep cycle. And then lastly, just like UV rays contribute to this, a ton. It's age-related macular degeneration. That is, when we're talking to patients about, protecting their eyes over the course of their lives, right? That UV damage and blue light damage is cumulative. It stacks up basically over the course of your life. And so even though, sometimes it's like, you see an elderly person and they're starting to have macular degeneration, and you're like, oh my gosh, you really need this filter. It's probably more important to prevent that earlier on, right? So even when they're a child, through their adult years, it's really important for people to begin to think about this, right? Because people live longer and longer. They want to be in their old age being able to see, and this is one of the biggest things we can do, easiest things we can do to make that happen, right? Is having these the UV protection and the blue light protection over the course of their lives. So those are, just kind of a quick recap of the light spectrum, blue light. Um, what I want to go back to now, I want to kind of talk a little bit about the reading parts where it talks about the index of refraction. So let me pull up that. I think I'm going to go back to the book again. Where am I? Here. Okay. So these are the parts here. It's down a bit, sorry. Oh yes, we have the different waves of okay, cool. So and I think there's, sorry guys. Oh yes, and then there's the formula down here. Okay. So things that are important to have observed or have kind of gotten out of the reading here and out of the audio recording is basically that when light comes down or comes into a lens, right, or a material, it's going to slow down, right? And what refraction is when the direction of the light entering this material or this medium is changed. Okay, so think about it as the light being bent in some way. Okay, so I believe we have some pictures here where they're, kind of trying to illustrate that, right? That it's coming in. to the medium, or in most of our cases, it's going to be to a lens. And then when it exits, it's exiting at a different angle, right? That it's bending. Now, it's a little, I think, for our purposes, thinking about, the speed of the light or how it's slowed down. I feel like that doesn't make as much sense when we're just kind of talking about this in terms of optical. Um, but it is important to kind of know that we are talking about the speed of light a little bit, just because if you look down here, um, basically to find the index, right, of a material, or the index of refraction, it's actually really talking about the speed of light in the air versus the speed of light in the material, right? So that's why they're kind of talking about it, in terms of speed. But for us, I really think it's helpful for us to think about the light coming in and then bending, right? Or going in a different direction, right? So basically, if you take a look, let me just make sure that I covered what I wanted to there, just looking at my notes. Yeah, just, you want to think about when you're looking at these materials, right, or these different indexes, you want to think about them in terms of how much are these different materials bending the light, right? Are they bending the light, not at all? Are they bending the light just a little bit? Or are they, effectively really, changing that light and changing the angle of it? Okay. Um, so I will tell you that these indexes, right, of, especially I would say the ophthalmic materials, right? Um, Probably less so the cornea and the lens and the vitreous, right? But of the basically the ones that you would see a lens made out of, these are things that you really should memorize, right? You should make yourself flashcards, because these are things that will be asked, most definitely, on the test, right? Knowing, what is, what is the index of refraction, right? Of polycarbonate, what is CR39 plastic. I would say it's unlikely they would be asking you about flint glass, but they may ask you about crown glass. So those, even though that seems kind of obscure, I would just give you a tip that those ones are most definitely going to come up on the test quite a bit. Obviously, high index is fairly easy for us. We just talk about it by, the index of refraction, 167, right? We're, constantly saying that. So that one should give you a little bit of a leg up. We don't really talk about the index of poly that much. I would definitely, if you're only going to kind of remember two of these, I would choose polycarbonate and CR39 plastic. If you are not in optical frequently, I will tell you, CR39 is an extremely common lens material. It kind of was what everyone would use, I would say, back 30, 40, well, maybe no. There was a lot of glass, that was used at first. But basically, when things moved away from glass, glass is quite heavy, right? But when things moved away from glass, it was, very, very common to use CR39. I would say a lot of optometrists, maybe not most, but if you go to an optometry office, oftentimes they're using polycarbonate, just because it has superior UV protection. It's also impact resistant, right? So some of that material is in or was in basically the reading that I gave you, more on the optical side. But those are really the two that I would focus on, is the CR39 and the polycarbonate, for knowing what those indexes are. I do believe they come up again in the reading, but definitely super important. What else do I want to talk to you about? Okay. So just kind of plowing through this book a bit more. I know we talked about this briefly last week, but definitely important to know, be able to tell where the apex of a prism is, where the base of a prism is, knowing that when light, and this is shown kind of over here where it says the B side, or I'm sorry, in diagram B, it's showing you how the light is going to be bent towards the base of a prism. When light goes through it, that's important to know that light is bent towards the base, okay? Definitely, you'll probably encounter a question on that. The other thing, I don't know that you will actually see a question about this, but it's very helpful for you to know this, just because we do work with prescriptions with Prism, and you guys see Prism being prescribed, at least on a weekly basis, I would say, probably more than that. But you want to think about it as the base of the prism should go in the direction that you would like the eyes to ultimately go in, right? So, if you're wanting, if you're kind of imagining that the eyes are going to need to kind of converge, you would think about that as, the big part of the prism, the base of the prism is going to go, in that direction. So I think that is helpful, when you're looking at a prescription. It may explain to you kind of, what that prescription is trying to do for the patient. What else is really important about this? So just going down a touch, again, both in the audio and obviously in the book, they talk a little bit about this. It says basically that if an object is 1 millimeter, 1 meter from the prism, the image of the object through the prism is displaced 1 centimeter. Okay, so they give you this formula saying that if you're looking at something through a prism a meter away and it jumps over 1 centimeter, that means that that is equal to 1 diopter of prism. Okay. They're not going to ask you on the test, like, okay, you need to calculate that, or, it's really most likely they're just going to kind of ask you, okay, what is that formula, right? Is it, 1 centimeter to 1 millimeter, or, is it, I'm sorry, to 1 meter, or, kind of just referring back to what basically knowing that formula. So, definitely something you should have in mind. Yes, okay, so this stuff is a little more tricky. Let me see. I do want to talk about it. I just didn't know if there was a picture of lenses here. Well, we can kind of use these for now. I do want to talk about these images one more time in a minute. But basically, another key thing to know, right? This is going to come up very much when we talk about this next week, but or for our next class. But basically, you want to be aware that a plus lens is going to effectively be two triangles placed base to base. Okay, so this would be a converging lens, a plus power lens, whereas a minus lens is going to be two prisms or two triangles, right? Placed apex to apex. Okay, so that's going to be a diverging lens, right? So definitely important that you are aware of that, because when we take a look at how to determine, which direction the prism that's being induced is being induced, you're going to need to know, what a minus lens would look like in terms of prisms and what a plus lens would look like in terms of prisms. So definitely try to internalize that. All right, so now it goes, this is a little bit more technical, but not really too bad. But basically, what you want to think about towards the end of this chapter is they talk quite a bit about what happens with light when it goes through these two different types of lenses, right? So they talk a little bit about when light comes in straight through basically a converging lens or a plus lens. How does it move and where is the focal point, right? And then they talk about it in terms of a minus lens or a diverging lens, and they talk about that lens's focal point. So this can be fairly confusing. One of the things that I want to do for it is just briefly share my screen and hopefully, give a little kind of explanation of it. Let me just stop this. I'm sorry, I didn't mean to share my screen. I meant do a whiteboard. But let me just take a quick snip of these to show you what I mean here. I'll save it. Okay, and then let me do a whiteboard real quick. Okay. Perfect. So basically, let me just see if there's a way that I can just put this picture in. I don't know if I can draw over it if I do, but let's try it out. Oh, that's not the picture I wanted, sorry. I guess I didn't save this snip. Okay, let me try one more time. Okay, it's very small. Okay, so this basically talks about the converging lens, right? The I'm sorry, the plus lens. So what is critical here, right? And this, I found this to be kind of it seems like a simple concept until you get to the minus side of things. But basically what they're explaining to you is they're explaining to you, and I'm just gonna try to draw over this and see how that goes. But what they're trying to say is that when light goes into a plus lens, it's going in, I'm going to just make some arrows. It's going in like this, right? And kind of going through these two prisms, right? And we already know that light is going to be bent towards the base of the prism. So think about it going in, and then this doesn't look like a very dramatic bend, but it's basically being, sorry, not so good here. It's basically being bent again towards the base. So it comes in bending. All right, and it goes through, and then it comes out over here, and it's going to go to a focal point. Okay, so you might be wondering, why do they say that it's a real focal point? And that will come into play a little bit later when we just talk about the minus lens. But basically what that's saying is that with a converging lens, we we're interested in basically the focal point, the real focal point of the lens, and what that is. Like basically at 1 meter, that's a very critical measurement. And then if we look at really quickly, just how does that differ from a minus lens? Let me just take a quick snip of that so I can pull that up. Save that too. But what they're saying here as I upload is that it's going to be 1 diopter of power if the focal point is at 1 meter. Okay, and that's going to help us to figure out the power of lenses, which comes up a little bit later. Okay, so now here, maybe I can get these both on this same page, but here we have our minus lens, right? And so if we go ahead and look at the light rays coming through, very, very similar to the plus lens, they're coming through, they're going in, and then they get bent this way, Okay, so they're coming in and then they're again still bending towards the base. So all of that makes sense, just what we know. And then what's happening is the light rays are then diverging rather than converging as they are in the plus lens. So they're really just kind of think about them as spreading out. Okay. Now that all makes sense. The only thing is how do you figure out the focal point, right? So if it is diverging the rays, we don't have a focal point over here, right? So the problem becomes we actually have to kind of backtrack. And maybe I'll change the color a little bit here so you can see. But what they've done is they've traced these light rays that come out of the diverging the diverging lens, and they've traced them back this direction. So they're going back here, right? So they're like, okay, this is a straight line. We're not bending, we're just tracing all the way back from starting here, right? And then going through the lens, and they're finding what they call the virtual focal point. Okay. So what's really strange, and this is an odd concept, right? But they're saying that there is not a real focal point with a minus lens, but in fact a virtual focal point. And the reason for that is because a minus lens diverges rays, and so they're diverging from basically the virtual focal point. The focal point is actually behind the lens, okay? Which is kind of a strange idea, but hopefully kind of seeing the pictures of it. When I was first looking at these images, like in the book, it didn't make a ton of sense to me because I couldn't quite figure out, okay, which direction is the light going? What are they talking about here? So hopefully having some of these pictures and some of the lines and kind of talking about tracing the rays makes a little bit more sense. But that's kind of this idea of a virtual focal point versus a real focal point. So kind of an odd thing. But let me I just want to quickly review my notes here just to make sure that I said everything that I wanted to. I think pretty much. So, so that definitely is something you'll want to, have an understanding of. Definitely will hopefully you'll understand a little bit kind of the negative and the positive as we go forward and do calculating focal lengths. The other thing that I just wanted to quickly show a picture of and kind of go over is talking about the plus and the minus quadrants of the lenses briefly. So I'm just going over my notes here because they do talk a little bit about that as well. So I think maybe I'll show that on the whiteboard too. I'm just going to take a quick snip so I can show you guys that picture. This is just from the book to, just going to scroll down so that I can put in the image. Sorry. Okay. So this may look a bit familiar as well. But basically they're showing over on the left side, they're showing the plus lens, right? The converging lens. You see the real focal point over here. You see the light rays coming in on the left. And then on the right, they're showing the diverging lens, the minus lens. You're seeing the light come in and then diverge towards the base of the prism once it's come through, and then you see that they're tracing it back. So the other thing, just, it's basically the same here, but they are showing you just kind of the positive and negative focal areas of the lens too. So thinking of positive, over here, on the side of the lens where the light is coming through, and then the negative as being behind, more probably significant for the minus lens and this virtual focal point. Okay. So let me kind of, I'm gonna create a new whiteboard, I think, for our next piece of info. The next part of things gets into how do you figure out the focal lengths of a lens, basically dependent on the powers. So if you remember, we had a series of kind of practice questions about those. So let me, I'm gonna just, let's see what the best thing is. I guess I could just scroll down, probably makes the most sense. All right, so the first question that they actually, you know what? I'm just going to put up the practice questions that they had here. And I'll tell you this again, um, you know, later, but basically it makes a lot of sense to practice calculating um, focal length. It's just something that kind of like Prentice's rule and stuff that you start to get good at once you've done it a bunch. So basically, what they're doing here is this is just from the book, right? Like just a snip from the page of the book. And basically, what they're asking us to do is they're telling us the diopter power of the lens, super significant to pay attention to whether it is a minus lens or a plus lens. So thinking about it, whether it's the, plus quadrant of the lens versus the minus quadrant. And what they're doing is they're asking us to figure out basically from this power what the focal length is. Okay. So the thing that's really important here, and this kind of goes back to what I was talking about earlier on in the class, the thing that's really important is being very good at converting between meters to centimeters to millimeters because they'll ask you it in all sorts of different form, like incarnations, different forms, or different measurements or units of measurement, I should say. So what they're telling us is the pretty simple formula, right? So they're telling us that for the formula, the focal distance, so F equals 1 over D. Okay, so D being the diopter power. Okay, so if we were to do, I think their example question was telling us that the lens was a +2. Okay, so pretty simple. What we're going to do is do the focal length will be 1 over +2. Okay, so basically what I'm doing here is putting my lens power into my formula. And then if we took a calculator, always nice to just double check by using that, and we divide 1 by 2, we are going to get that F equals, and again, we're going to be making sure to preserve our sign so that it is positive. We're going to get that it equals 0.5. Okay, so we know that when this formula is done, it must be done in meters. Okay, so in this case, I'm going to remind you that it would be very helpful to write that it's 0.5 meters. Okay, now what most of the questions in the test are going to do is they're not going to have it for you in meters. So they're going to ask you, what is it going to be in centimeters? What is the focal length in perhaps millimeters? So you're just going to need to be really good at knowing how many centimeters are in a meter, so 100, how many millimeters are in a meter, 1,000. And so depending on what form that they're going to ask for it in, you're just going to be thinking about converting it, moving it over, 2 decimal points for the centimeters, and then over 3 decimal points for the millimeters. Okay, so if we were to go ahead and do this one, we would go and we would say, okay, a half meter is 50 centimeters. Okay, or it's going to be 500 millimeters. Okay, so think about it. I know it's been quite a while since a lot of us have done place value math. That was something that, definitely comes up in elementary school, kind of like my son was working on this. I think they talk a lot about this in like fourth grade, I would say. So, basically, you just want to get used to reminding yourself, okay, if we're going to, the 100th place, we're going to be hopping over 2. If we're going to the 1,000th, you're going to be hopping over 3. Okay. So just to kind of connect these guys to here. But definitely just, being confident with the conversions is key here, right? Because the formula itself is like super easy, right? One, you're dividing one, over it, basically 1 over the thing. So if we were just to quickly go through, say we're going to do the one just real quick for -5, if we wanted to talk about that one's going to be more of a virtual focal length or focal distance. So what we would do is we would do 1 over -5. And what are we going to get here? I'm going to use my calculator. So we're going to get minus -0.2 meters, which would then be 20 centimeters or 200. Oh, sorry about my writing here. 200 millimeters. Okay, so my thought would be to go through, these are the practice questions that are right in book 2. Go through those and just practice, and don't just get it in meters. The thing that you really need to feel confident in is converting it into centimeters and then converting it into millimeters too, because the multiple choice will usually not be in meters. You may get one in meters, but you'll see them in centimeters and millimeters too. So that is, oh, did I keep it? Yes, I did keep it minus. So again, that's important to keep the sign as well. So, that's kind of for getting the focal distance from the diopter power. Now, if you were to, the next step of this was, okay, if you have a focal distance of X, what is going to be the diopter power of the lens? So it's basically extremely similar, just kind of going backwards. So let me take another quick snip of the practice questions for that. Again, these are right in the book. If I'm just going to add them to my whiteboard again. Okay, so now you're going to be seeing the distances, right? Rather than the diopter powers. The formula is startlingly similar. So you're going to have, I'm sorry, not the, I should get rid of that. How do I erase that? Is there like a, all right, never mind that, sorry. So it's going to be the diopter power equals 1 over the focal distance. Okay. So what you would do in this case, I think the example that they gave in the book was they were like I'm sorry here, I'm looking at my wrong example. Okay, so the focal distance is 7.7, so positive 7.7 centimeters. Okay, so in this case, we do have to, again, convert it into meters. So now you are going to kind of be going the opposite direction, right? You might want to think about it as, dividing it. So we're going to go ahead, and before we can do anything, we have to make sure that this is in meters. So if we go ahead and do that, we're going to move it over 2 decimal places because there are 100 centimeters in a meter. So we're going to be getting positive. Again, that's critical. And you're going to get 0.077 meters. Okay. In which case you are then going to do 1 over 0.077. I will do real quick. Which comes out to an odd number, which would be, again, we're going to stay in the positive here, 12.987, which you could just say is 13 diopters. I am going to remember that it's positive. So you could do like a little D for that. Okay. So basically that's telling you that if you have a focal distance of plus 7.7 centimeters, that is going to be effectively a 13 diopter lens. Okay. So you can see again where being able to convert quickly from, either millimeters, to meters or centimeters to meters is really critical because, the math is not going to come out correctly if you're doing this without converting first. All right, so just real quick, if we were to do, let's see, one that is not in meters already here. I'm just looking at my practice ones. Let's say that we do number 12. Okay, so that one is negative 33 centimeters. So we would, again, we have to be careful with the sign, but if we're starting with 33 centimeters, the first thing we have to do is convert that to meters. So we're going to go ahead and we're going to do, that's going to become negative 0.3. I'm sorry, that point disappeared there, 0.33 meters, right? So basically like a third of a meter. Then we're going to go ahead and do 1 divided by 0.33. Let me do that. So we're going to get an answer of, again, I'm going to keep my negative point, I'm sorry, 3 point, it actually comes out kind of weird, but 3.03, which would be the equivalent of negative 3 diopters for this one. Okay, so not anything too crazy. Again, the formulas themselves are like insanely easy. It's just making sure that you convert in the correct direction, right? So the thing to remember is that if you're trying to get the diopter power from a distance, you have to convert first. But conversely, if you have the diopter power and you're trying to get the focal distance, you convert after. Okay. Well, if you need to convert after, or if you need to convert in general, think about it as, if you start with the distance, you got to put it into meters first. If you start with the diopter power, you have to put it into, either the centimeters or the millimeters after, if the question is asking you, to convert it beyond meters. Okay. So that one, again, that's just something you want to practice with. My thought is to, go ahead and, go through these practice questions, just, get really comfortable with it. Some of these, are starting in meters. So, don't be fooled. You don't have to do any sort of conversion of that. Those are super duper simple. So definitely, keep your eye out, from where your starting point is. So let me show you just real quick a couple of the questions that you might see along those lines, just so you kind of know like a little bit what to expect here. So again, I'm just going to quickly snip a couple of what these might look like. And you'll see kind of what I mean about just being super careful not to get tripped up on the conversion part. Let me just make this a little bit bigger. Okay, so some questions that I pulled from practice tests. What is the focal length of a 10 diopter lens? So you can see here that they're giving you a million different scenarios that look very similar in all sorts of different measurements. So, so that's fairly tricky, right? So even though the formulas are easy, it's like, all right, where are you going with that? So you do 1 divided by 10, you would get 0.1 meters. Now that is not 0.1 centimeters, nor is it 1 meter. 0.1 meters is going to be the equivalent of 10 centimeters, okay? Because if you said, okay, there are 100 centimeters in a meter, you're going to move that over 2 decimal points from 0.1, it's going to become 10 centimeters, okay? So that's where things get tricky, right? Hopefully that illustrates that concept pretty quickly as to why you need to be good at converting, because they're clearly trying to trip you up here with a couple of those answers. Other ones that you might see, they spelled it diopter rather than diopter. So you'll have to excuse that, but basically they're starting with 1,000 millimeters here, right? Okay, so this one is they're telling you the distance, they're telling you what the focal length is, they want to know what the diopters are. So you can't just, jump right in and do it in millimeters. You have to first convert that to meters. It should be easy to know that 1,000 millimeters is 1 meter. So you're basically dividing 1 by 1, which is 1. So in this case, it's going to be a 1 diopter. Okay, so that's why you have to convert first on those. And then again, here you can see the focal length of a 5 diopter lens. We're going to do 1 divided by 5. It's going to be 0.2 meters. Now they don't give you well, they do give you a meters option. It's not correct. It's not 2 meters. It's 0.2 meters. So then you're going to have to convert that. That's a tricky one. They're showing you in inches, but they're so that's a toughie because you'd have to know how many centimeters would be in 40 inches. But basically, luckily, you don't have to worry about that, because if we have 0.2 meters, we're going to move that over 2 decimal points to be 20 centimeters. So in this case, you would be looking at the 20 centimeter answer. It would be A. Okay, so yeah, so those just give you, a little bit of a taste for what that might look like. And then I did just want to quickly show you 3 more questions that related to what we just talked about here. Okay. Similar, so kind of talking about how to calculate prism. If a prism can displace an image 1 centimeter at a distance of 1 meter, it is said to have a power of how many prism diopters, right? So this one talks about that rule that we read about in the chapter. It would be 1 prism diopter, because remember that, if you're looking through a prism at an object that's 1 meter away, it should displace that object 1 centimeter. Okay, so that's, an example question about that. I don't expect a lot of questions about that, but that's one that, you might see. If a converging lens has a power of 2 meters, so again, this one is quite similar to what we just did here. I feel like I don't probably need to go into this one again, but, oh, I think the reason I put this one in is because you have to be really careful about your powers, okay, or like your positive and negative. So just if we quickly did this one out, 1 divided by 2 is 0.5. Now, obviously, there are 2.5 options, so you just have to be really careful that you're not doing the minus because here we are with a plus lens. Okay. And then lastly, a diverging lens produces a blank image. Okay, so that goes back to what we talked about a little earlier with the virtual focal point. Okay, so remember that a converging lens is going to produce a real image, a real focal point, whereas the diverging lens, because the rays are diverging out of the lens, that they're going to trace those rays back and find the negative or a virtual focal point. So that's, kind of referring to what we saw there. So, so that's the end of the super technical stuff from this chapter. So, hopefully that explains things a little bit better. We don't have a ton of time left, so I did want to spend some time quickly going over the other reading that we did. So I'm just gonna get rid of this whiteboard and share my screen so that we can look at the, in my opinion, more fun optical part of things. Let me find it here. What did I give you? So this is the PDF, and I'm just going to share this again so we have something to look at. This is the PDF that looks like this. Hopefully it's loading. The one that had a lot of stuff about lenses in it. So I'm just going to kind of trying to make this bigger here. Just going to kind of go through it and talk just as we kind of skim through it, talk about some of the really important parts of it, the parts that I want you to be kind of internalizing. Does talk a little bit about refractive index, talks so okay, so the other thing that this gets into, which is really, really important stuff as well, is it talks about, so there's a little bit about specific gravity. Um, I think honestly, I have to be honest with you, I can't remember too well if there was much on specific gravity on the test, but I really don't think that was a large part of things. It's much more about Abbe value and index of refraction. So I guess personally, I would not worry too much about specific gravity. But basically, what it goes over is this is a pretty critical concept, Abbe value. The thing that that you will hear, and if you are in, kind of in the optical world for a bit, opticians love to talk about chromatic aberration and how poly is a crappy material. um, and so you'll see that, like, if you're on like opticians of Facebook or whatever, they're always like, dissing polycarbonate. But the reason being that it has, really kind of a bad Abbe value. And what that means is that you are likely, especially in higher powered polycarbonate lenses, to see chromatic aberration, which is like colored halos. The best way I think I can describe it is to kind of describe it as like colored halos around an object. So if you ever have a patient with a fairly high powered poly lens, you could take a look at their glasses, and the best way to see it is to kind of look at the thick part of their glasses. So if they're in a minus lens, or in a higher plus lens, it's it's usually going to be more prevalent towards the outer areas of the lens, right? So if you look through it at kind of an angle on the side, what you might see is like kind of a dark object might have like a slightly yellow kind of like halo around it, right? And that's because just poly isn't like the most pure material optically. It has a high Abbe value, which is not considered to be very favorable. So basically, I'm sorry, a low Abbe value. I apologize. The low ones are not going to be good, whereas the high ones are going to be more preferable. So you can see that one of the reasons, and I was kind of saying, oh, like a lot of optometrists don't use CR. as their material of choice. But a lot of opticians would say, oh, like we only use CR just because of this ABI value that it has. Like it has, pretty much like the best ABI value aside from glass. Right. So that means that, aberration wise, it's gonna, be very minimal. Um, However, it's not impact resistant and doesn't have the same UV protection that poly does. What people often will use is Trivex in terms of kind of a replacement for that, or something that kind of is somewhat in between. I mean, Trivex, for all, people complaining about poly, is actually not, what is it, like 13 or so different. So it's not like it's like night and day better. But, oftentimes people, will recommend that. We don't typically recommend that just because it is a bit more expensive than poly. And, it's just one of the things that we do is we're trying to keep the copays a little bit lower, but we have a stock of polycarbonate, and it's hard to kind of stock poly and CR and Trivex and 167. So sometimes you just kind of have to choose what you're going to kind of get behind. Other than that, you can see that higher indexes like 170, we don't use 170, we usually use 174 if we're going to use it. But that has not the most desirable ABI value either, although I would say a lot of people like 160 or a high index will have usually a slightly better ABI value than poly will as well. So if you ever have like an optically sensitive patient, someone who kind of complains about seeing rainbows or something like that in the lens, definitely moving away from poly. Usually it's going to be something where we go to like a high index, is a good recommendation for that patient. All right, what other things should we talk about? Okay, so it goes through, what the pros and cons are of every material. Definitely important to, know in general. They do talk a lot about like crown glass that, I hate to kind of like talk about the test always in kind of a negative way, but they do talk a lot about crown glass, which is like kind of weird because no one uses it. And whenever you try to, like, you have a patient come in and they're like, I want glass, it's like the hardest thing in the world to actually get them glass. And it takes like 4 weeks and it's just, kind of a pain in the neck. So, why the test talks a ton about glass, I'm not entirely sure. But it is definitely something that you will see on there. But obviously, there are some impact resistance issues with making lenses out of glass. It is heavy. It's super hard to scratch, which is awesome. But it tends to be generally because of the heaviness and the lack of availability, something that we're not usually using. CR, much lighter weight, nice ABI value, um, less, kind of internal reflections than something that is of a higher index. The higher the index, the more internal reflections in a lens. So that's important to know. Poly talks about it's higher impact resistant. It is thinner than CR. One of the things that will help you is that if you look at the index of refraction, it will give you a tip on what is thicker and what is thinner. Okay, so obviously we're rounding up to 159 with poly. The higher this number, the thinner the lens is going to be. Okay, so that means that CR is going to be thicker than poly. Trivex is going to be thicker than poly, whereas any kind of high index is going to be thinner than poly. So as the opticians know, typically over a 3 in power, whether it's plus or minus, we're looking into a higher index material, so it'll be thinner. One of the downsides, or one of the things that you have to consider when you're doing a high index, is that it does have more internal reflections in the lens. Most likely, I probably should know this, but most likely because of, it's bending the light more, right? It's higher index, so it's creating more reflections inside the lens. Now, the thing with poly is that it is quite soft, right? So when we talked about glass being hard to scratch, poly is quite easy to scratch. So that's why you really, we do uncoated poly sometimes, when patients really don't want anti-reflective coating. But in general, that hard coat that comes with the anti-reflective and those layers and the dust resistance, the oil resistance that comes with anti-reflective coating, those are going to be super, super helpful to have on a poly lens just because it is inherently a little bit more scratchable than one of CR or a glass lens. So anyone who's slightly rough on their glasses is gonna, really benefit from that with a poly lens. What else? High index that also has UV, so that's excellent. Better ABI in general, although they're saying it ranges. We saw some high indexes in that chart that had really nice ABI values, others that were right around polys. And then obviously it's going to be thinner, it's going to be lighter. So that's good. Has superior impact resistance to glass. However, it's not going to have the same impact resistance that Trivex and Poly will have, right? What else? Trivex. A lot of people like Trivex a lot. One of the reasons we don't always go to Trivex is that it is thicker. So it has a little bit less range than poly, whereas you can kind of get away sometimes with like a -4 or so in poly. Trivex is going to be noticeably thick, even at a relatively, I don't want to say -4 is low because I find that to not be a low script, but like even at a prescription that's moderate, let's say like a -4, it's still going to be a bit thick. So, but it is impact resistant. It is light. It is more scratch resistant too. All right, so then we go into kind of pushing right along here, but then we go into the different lens coatings. I find the differences in anti-reflective coatings, like I find that to be really interesting. I put in that video for you guys from Lara McKay about how anti-reflective coatings are produced and how they kind of scratch test them, like quality control them. I find that video to be like just super interesting. I like seeing like, how they vaporize the chemicals and how they do the different layers on it. So if you haven't taken a look at that, definitely watch that video. They talk about the different coatings, if it's something that's dipped right in, pretty straightforward. If they're spinning the coating, kind of while spinning the lens. What is this? In mold coating. Okay, adding a hard coat to chemicals to the lens substrate while the lens is being formed in the molding process. Huh. I have to tell you, I don't know much about in mold coating. And then vacuum coating, right? So that's the one that is featured, prominently in that video. Definitely super, the nicest coatings are done in a vacuum chamber. Super expensive for the labs to invest in that, those chambers and that level of manufacturing ability, but it definitely, produces the nicest coatings. All the crizals are going to be done like that. Basically any lab that, knows what they're doing is going to have vacuum coating for anti-reflective coatings. And that's what we use in the office. We're not using spin or dip coats. All of them are vacuum coatings. So what else? UV. So lenses can have, like, they have inherent UV protection in the material, right? Just like with blue light filters, you can have a blue light AR, but you can also have a blue light that's inside the lens material itself. Before you recommend that, just know that it's less available with vision plans. So don't get yourself into trouble, but it is very nice to have it in the lens. And yeah, so the other thing that they can do is they can put a UV coating. If you're getting a nice anti-reflective coating, that's just going to come, it's going to be one of the layers in the anti-reflective coating. But that's definitely, something to know is that they can really make that 100% like really like an armor coating of UV by having that UV in the lens material itself, but also be like another layer in the coating process. All right. So tints, right? So the big thing for our purposes, tints versus polarization. We'll talk a little bit more about polarization. The thing to remember about tints is they're really going to make stuff darker, right? That's like that sounds dumb, but just think about it as darkening things, right? Like in general, we're using them for sunglasses, but it's not going to do anything to cut glare. It's literally just going to make less of the light, kind of pass through because the lens is darker. Okay. Um, so, they talk a little bit about this is an interesting idea. Dark sunglasses actually letting the pupil dilate to have more, UV rays or maybe even more, well, I suppose, yes, more blue light get into the eye. I- Seems a little suspect, but because that almost says that it's like not a good idea to wear sunglasses, which doesn't make a ton of sense. But I guess they're trying to point out, that you need to have UV protection. Now, when we're doing sunglass lenses, most of the time we're doing polarized anyway, which we'll talk about. But if we are doing poly, which is what we use, polycarbonate, that's going to have UV protection in it as well. So, not something that they'd need to worry about in our offices. Talk a little bit about the tint styles. There's solid. Typically, we would be doing like an 80% tint here, which means that 20% of the light goes through. In this case, they'd fade it down to be light at the bottom, just has a nicer look to it or a different look to it. This would be a double gradient tint, so obviously it kind of is, changing colors. Sometimes like with the Maui lenses, if you guys have seen like the Maui Gym sun lenses, they actually do like a tint like where they lighten it up in bands in different areas across the lens. So you'll see like kind of sometimes it'll be like lighter in the middle, which is kind of weird, and then tinted dark like on either side. So that's, there's lots of stuff that can be done with tinting. They talk about the tint densities. Again, typically we would be doing 80% gray or brown. In the past, we don't do a lot of this now, but in the past we would do what have you. So if someone came in and was like, I would like a purple tint on my lenses, we would say, all right, cool. And we'd do like a 20% like violet or something, just, depending on what, sometimes it would be like older women that would want like a slightly warming tint, like a pink or like a rose was something that sometimes you'd hear requested too. But that would be in like the 20% range. So you could see it like a little, but like not that much. They talk about different color benefits. Um, Definitely interesting stuff. I wouldn't worry too much about this on the test. The thing that I don't love about the color stuff is that I've heard conflicting things. Like it's not like this is like how it is. It's kind of like sometimes you'll hear, oh, like pink can be used for this. And then you'll hear another source being like, well, actually it's used for this. So, that kind of is not my favorite about it. Um, but, it is, some people definitely believe very strongly in this. One thing that you guys have probably seen in the office that relates to tints is the FL41 tint. It's kind of like this reddish, like orangey, almost brown tint that can be. I believe, there's been some research that shows that it can really help with migraine headaches. So there are a couple different manufacturers that will do that tint, and some people really swear by it that, just kind of blocks the overhead fluorescent lights, helps outside too, just with, reducing headaches and migraines. So, That's one that you might see. One thing I would say is I remember, oftentimes patients would come in and be like, well, what has the best colors, right? Like, meaning like what has the most accurate colors or what is going to look the best, when you look through it. I feel like that's subjective, but if they're looking for the truest colors, right? Like something that's not going to change how you see colors, not going to mess with like your photoreceptors, right? Like your rods and your cones. It's going to be the gray, right? So if you have someone that's, fairly particular about that, I would not recommend the brown, definitely, or the green. You definitely want to kind of stick to a gray tint if you have someone who's a bit on the pickier side. All right, so other thing that is really interesting is photochromics. They have gone through a lot of different changes over time, since like I would say the 60s and 70s, since they came out. They've gotten better and better. The thing that sometimes you'll hear patients say is, "Oh, I hate how long it takes to change when I come inside." But and it depends. Like, sometimes, especially like kind of when it's like different extreme heats, whether it's really cold or really warm, you can see that things do take longer to change. But that's definitely something that, excuse me, that kind of has lessened, over time. It's definitely not something where, 10 minutes later you're inside and it still looks like your lenses are gray. So, not as much of a worry. Lots of different kinds. There's extra active, which, works behind a UV screen, like behind your windshield. There's, the regular ones. There's, lots of different ones. There's even like a polarized transition. So, sadly, we do have some availability issues with those. So, before you're kind of talking about them with a patient, you just want to make sure that it's something that we can get. But, um, kind of neat stuff there. All right. So, things with that you want to know about photochromics. You want to know what the active ingredient is, which I'm trying to scan because you can see that I've really, yes, really remembered this well. It's silver halide. Okay. So this, I remember specifically this being on the test. So there's just lots of like little kind of bits and pieces that you want to know. You want to know what the active ingredient is or kind of the thing that's like making transitions change. Um, but whether you need to know about photochromic film versus like stuff that's like imbibed into the lens, I wouldn't worry too much about it. Wow, this is in depth here. All right. Polarized lenses. So, this is an important thing that you want to, have kind of a general understanding of. Um, Basically, polarization is kind of choosing, the best way to kind of think about it is choosing like what light to let through, right? It's only going to let light from one direction come through the lens. Okay, so you could think about it as effectively kind of reducing, about half of the light that would normally, kind of be coming through the lens. And it's really, really, really excellent at eliminating reflections, right? So it's when you're thinking about something like a wet road, like sometimes in the winter, you know how like the snow like melts on the road and then the sun comes down on it and it's like, just kind of blinding. Polarized lenses are like amazing for that, right? They're also amazing for like if you have a patient who's like loves fishing or something like that. They just allow you to actually see through all of that glare, all of that surface light on the water. It's awesome, and you can just kind of like look almost like magic, like into the water. The thing to kind of describe it is like a almost like a Photoshop filter, right? It increases contrast and just kind of takes away like the noise kind of the reflections. So, um, talks a little bit about the different polarized filters, talks about a little bit about like lamination because these are actually like sheets that are laminated like with heat into, different layers of the lens. Talks a little bit about identifying stress. So if you hold a pair of polarized sunglasses, the easiest way to kind of see it is to hold up a pair of polarized sunglasses in front of your computer. I mean, there are also tools for this that, we have in the lab, but you can hold it up and you can kind of see, like if you have a pair of polarized sunglasses or if you see one at the office, try it out, hold it up in front of the computer screen, and you can see like any area where the lens is a little bit more bent, usually just because it's a little tighter in those areas once it's been like popped into the frame. So it's not necessarily something that the patient is going to notice. It's quite unusual that they would notice it, but it can show you different areas of stress or like the little pressure points where more of the lens is pushing against the bevel in the frame. All right, talks a little bit about mirror coatings, double gradient, solid. And then we talk about anti-reflective coatings. I have talked a fair amount about that. Things that you do want to know about anti-reflective coatings, it's addressing the reflections that are in the lens, okay? It's making light pass through the lenses better. It's not polarization, right? So it's not really reducing glare in the environment, okay? So it's kind of like a thing for glasses wearers, right? Like if you would be better off, and this is a weird concept, but you would actually have less glare if you didn't wear glasses, right? Than if you had glasses on. So it's kind of, it really only applies to when there's a lens involved, right? They use anti-glare coatings on paintings, right? So that you can see them better because they put glass on the front of them. Same thing with like photographs, right? So think about it like it's going to reduce reflections within the lens, but it's not like polarization where it's going to reduce reflections on like a roadway or like the water. Okay, so that's an important concept because a lot of people kind of confuse that, and I've heard, sometimes I'll hear people in the office kind of acting as though it's going to reduce environmental reflections, and it's really not going. That's not really the purpose of it. All right. What else do we have? Okay, so this talks a little bit about light waves. And this is a really interesting concept. I don't have much time, so I'm going to kind of quickly go through it as much as we can. But what anti-reflective coating does is it actually kind of causes disturbances or interference um, to allow the light rays to actually pass through the lens better. So when and this, I would read through this again to really get, a strong handle on this. But basically, what it's trying to do is it's trying to mess with this perfectly kind of like even pattern of the light rays and the reflected rays. And so when there's actually interference here created by the anti-reflective coated surface, it actually allows the light to pass through the lens much better with much less reflection. So it's kind of almost like opposite of like what you would think would be good, but it just kind of causes it to get those waves to be kind of like out of sync, and thus the transmission is improved. So last thing here is just talking about the oleophobic and hydrophobic layers. Anti-static, meaning like, so oleophobic and hydrophobic, it's like oil resistant, water resistant. Phobic, meaning, pushing it away, kind of anti-static. It's going to get rid of the dust and, try to keep stuff from sticking to the lenses. That's a huge cause of scratches when people kind of rub dust into their lenses when they're trying to clean them. You always want to rinse it off, with under the faucet, lukewarm water with, gentle soap, gentle detergent is really the best way to go to avoid, that dust kind of sticking on there. Polarized lenses with AR, it's kind of the best of everything. You have both the effects of the AR as well as the polarization. And then we know a ton about the blue light, so I won't go into this as much. We talked quite a bit about this already. So I know that we need to kind of wrap things up. I apologize that there was a lot of stuff to cover tonight, so it kind of went fairly quickly. But definitely, if you have questions, if you have comments, things that you're kind of wondering that we didn't get to go over, post those in Discord, let me know. And within the next 4 to 5 days, I will have stuff up for our next meeting for you guys to read and watch and take a look at. So thanks, everybody. Have a really good night, and I will talk to you guys all soon.
Thank you.
Thank
Goodbye.
you.
Bye.
Bye.